So continuing with Dedekind domains, last time I gave you some properties about them. For example, we saw these technical lemmas, and we saw that every ideal contained a product of prime ideals and so on, and that I can always take an ideal and find some other one such that their product is a principal ideal. So I said that we're going to try to make a group out of these ideals, and so here's the before we do that, we somehow need to generalize the notion of an ideal, because we're going to want inverses, and it turns out that the inverse of an ideal isn't quite an ideal, but it's something called a fractional ideal. So here's the definition 3.3.7. So let R be a Dedekind domain. And K, its field of fractions. A fractional ideal is a subset A of my field. So notice that in a field you have no ideals, but I'm talking about fractional ideals, so this isn't quite an ideal. So it's a subset A of K such that the following three things hold. I want A to be an additive group so closed under addition. An additive group, an additive abelian group. 2, I want it so if I multiply my set A by an element X, I want this to stay in A for every X in R. So this again is somehow like an ideal. Remember, an ideal is an additive group. If I take an element of my ideal and multiply it by any other element of my ring R, then I stay inside of A. This again looks like an ideal, but notice that I'm taking some random subset of K. Here's something that's slightly different. That means that there exists some X in R such that X times A is contained in R. So every ideal is a fractional ideal. Every ideal is an additive subgroup. For every ideal this holds, and if I just take the number 1, then I know that 1 times A, it's an ideal in R. So this always works. But what I'm saying is that I'm taking some special subsets of my field K such that it's basically an ideal, and I can think of this as X as I can clear denominators. So I can find one element which clears all the denominators in my ideal. So let me give you a simple example of this. So example, so if I let Q be some rational number, then what I'm going to denote by this is going to be the set of all n times Q, such that n is in Z. This is a fractional ideal. More generally, I'll use this notation. So if R is a Dedekind ring, and K is the field of fractions, K equals frac R, and I take some element alpha and K, I'm going to let this be the fractional ideal generated by alpha, which if I take alpha to be in K, then this ends up being just the ideal generated by alpha. So this is the set of all alpha times R such that R is in R. So I'm going to let this. And similarly, so this will be a fractional ideal. Similarly, for any ideal A in R, 1 over alpha times A is a fractional ideal. So this is a set of elements which look like an element of A times 1 over alpha. So this is again a fractional ideal. I should give you a warning about these fractional ideals. If A is a fractional ideal, and you have 2 elements in there, then it's not true. It might not be true. That x times y is contained in your ideal A, in your fractional ideal A. So this is maybe different from what ideals. Okay, great. I've sort of skipped a definition here. I somehow put it into here, but let me just record it for posterity. And this ideal that I've just defined here, we're going to call it a principal fractional ideal. So let me just record it. RB second domain KB frac R for each x in K. We call this thing, which I just defined above, as a set of x times R, such that R is in R. We call this a principal fractional ideal. Okay. So this extra freedom that we have by working with fractional ideals and not ideals allows us to turn this set, make a group out of this set. So we can make a group out of the set of fractional ideals. So here's a proposition, 3.3.11. So the usual setup R, Dedekind domain, KB frac R. Then I'm going to give this a name. The set JK of non-zero fractional ideals forms a group under multiplication. Let me tell you what the identity is, with 1 being the whole ring as the identity. So you should think of this as, essentially I've turned the set of ideals into a ring, but the problem is the inverse of an ideal might not be an ideal, but the inverse of an ideal will be a fractional ideal. So the reason I have to introduce fractional ideal is so I can have inverses. Once I have inverses, then I can make a group out of this. And this proof isn't hard. Well, it's not too long. So let me just note that if A and B are fractional ideals, then their product, A times B, is the fractional ideal generated by the product of elements. So to go back to the definition of what the product of two ideals is, and just go through and you can just change it for fractional ideal, and you'll see that this is again a fractional ideal. This is clearly associative because ideal multiplication is associative, and somehow this implies that multiplication of fractional ideals is also associative. We saw this in problem sheet 1, the associativity. So this is associative. So we only need to check the inverse exists. And I guess what the unit element is, but I've told you what I want my unit element to be. I want it to be that one. So let's check for inverses. So if A is a proper ideal, so first let me just do it for normal ideals. So if A is a proper ideal of R, then by theorem 3.3.5, we can find an ideal B such that A times B is alpha. And I could always find an ideal such that I could always find a B such that A times B was principal for some alpha. So setting, here's what I'm going to define to be the inverse of this. A inverse to be 1 over alpha times B. As I said in this example up here, this also gave me a fractional ideal. So A inverse defined to be this is the inverse of A. Just check that if you multiply A by A inverse, then you end up with the ideal generated by 1. So this is what happened if I started with a proper ideal of R, a normal ideal. So what happens if I start with a general fractional ideal. If A is just a fractional ideal, then by definition, we can find some x in R such that x times A is contained in R, and this is going to be an ideal. X times A is going to be an ideal, not just a fractional ideal. So this is an ideal. Let's give it a name C. Then A to the minus 1 is going to be x times C times. So this is a normal ideal C, so I know how to do the inverse for the first part, and then to get the inverse for the whole ideal, just multiply it by x. And I think this is not an x inverse, it's an x that shows up. So this is the inverse. Great. So I have a group now of fractional ideals. Let me just highlight what the inverses look like. So here's a remark in this group. It follows that if A is a fractional ideal, deal in R, then say just a fractional ideal. Oh, yeah, because I need memory. Then A inverse is just a set of all x in K. K being, as always, the fraction field of R. Such that x times A is in R. So this is what the inverse of a fractional ideal is. Just all the elements in K such that x times A is in R. Cool. What can we use this for? So now here's some nice. Now that we have a ring, now that we have a group of ideals, here are some nice corollaries of this. So this really starts looking like, working with elements. So here's 3.3.13. We can really start working with ideals as if they were just normal elements. If A, B, and C are non-zero ideals, in a Dedekind domain, and I have A times B equals A times C, then B equals C. So if I have, I can cancel out A's on both sides. It's cancelative, this multiplication. And the proof is just multiply on the left by A inverse to get the result. So yeah, this ideal, this, I should maybe say that this group JK is a group. It's an abelian group. Let me say abelian, in case it's not clear. But all of the things are always abelian. Similarly, here's another corollary. 3.3.14. If I let A and B be ideals. I'm saying ideals, so not fractional ideals, just ideals in the Dedekind domain. Then A divides B, i.e., you can write B as A times some ideal C. So this is the case if and only if B is contained inside the ideal A. So A dividing B means that B is contained in A. So somehow division reverses and becomes inclusion. And this is an if and only if. So proof. If A divides B, we have that B is something like A times some ideal C, which means B is contained in A. Just think of what this means, right? B just looks like some element of A times some element of C. A is an ideal, so every element of B has to be contained in A. If you take an element of A and multiply it by any other element, that you stay inside of A because A is an ideal. So the first bit is easy. Conversely, assume B is contained in A. Then by this theorem 3.3.5, we can find an ideal M such that A times M is principal. This is what this theorem was telling us, so we could always find the ideal to make such that the product is principal. So now, what does this mean? If we chain this up, I get M times B, which I'm assuming, since B is an A, this is contained in M times A, which is alpha. Therefore, C is 1 over alpha M times B. And this is again in R. Remember, this being in the ideal generated by alpha means that I can divide every element here by alpha and stay inside of R. So this thing, which is just I've divided out by R, this thing has to be an ideal in R. It's again, let's say, an ideal. So for example, it's a product of two fractional ideals. So it's again an ideal. So now the result follows from noting that A times C is just B. So if I take C and multiply by A, then I just end up with my original ideal. Great. So which means that A divides B. And lastly, let me just show you how this fixes our problem of factoring things uniquely into we talked about how we couldn't factor elements uniquely into irreducibles. So in a Dedekind domain, because the ideals are so nice, it turns out that every ideal can be written as a product of prime ideals uniquely. So here's the theorem 3.3.15. This is the big theorem for us. So let R be a Dedekind domain. Dedekind domain. Then every ideal A can be written uniquely as a product of prime ideals. I.e., in other words, I can write A as P1. I should put P1 to the, well, I'm going to stick to what I have in the notes. P1 to Pn with the Pi prime ideals. And I'm guessing in this notation, I'm assuming that they're not necessarily unique. Distinct. I could group them up and then just put powers here, which is what we'll do generally. But for the moment, I just want to, there's a product of prime ideals, and there could be some repetitions in here. It doesn't really matter. You could just group it up, and it could be a P1. You could have A being P1 times P1. So you could write that as P1 times P1 or P1 squared. Okay, so let's prove this. So first, let's show that every ideal can be written as a product of prime ideals, and then we'll do the uniqueness. So first, we show that every ideal can be written as a product of prime ideals. So again, assume for contradiction this is not the case. So then let's consider the set of all proper ideals which are not a product of prime ideals. Then the set, did I give the set a name? No. The set of proper ideals which are not a product of prime ideals must have a maximal element or maximal member as R is Noetherian. So this is this Noetherian part, the third equivalent definition of Noetherian again. So I'm going to just give this the element of name, let B be this maximal element. So B must be contained in some maximal prime ideal. Then B must be contained in some maximal ideal. Maximal ideal. Okay, every ideal is contained in some maximal ideal. It's proper ideal. So maximal ideal P. Remember, all of my prime ideals are maximal. So I'm going to call it P. You usually maybe think of prime ideal, but here they're the same. So it contains some maximal ideal P of R, which I call it also prime. Then by corollary 3.3.14, B being contained in P means that that P divides B. So by this corollary, we have, the corollary told us how primes dividing. I'll just go back up to it. That A divides B if and only if B is contained in A. So if you apply this with the ideals B and P, we have that B is divisible by P, so I can write this like this. So this implies B is contained in this ideal C, and this containment must be strict. So they can't be the whole thing. Otherwise, B would equal B equal C, then which would imply that B equals B times P, which by the corollary before this one, 3.13 would mean, because we can cancel out, P is the whole ring, which can't happen. As I've taken P to be a proper ideal, as P is proper. Okay, so I have this containment. B is contained in C. It can't be strict. It can't be the whole thing. So what am I going to do with this? So notice that B was the biggest, by construction, B was the biggest ideal which was not a product of, which could not be written as a product of prime ideals. So anything bigger than it must be a product of prime ideals. So C, in particular C, must be a product of prime ideals. So since B is contained in C, C must be a product of prime ideals. So then P times C equals B is also a product of prime ideals. Right? C is a product of prime ideals, and now it's P times a product of prime ideals. So this is a product of prime ideals, but now this tells me that B is a product of prime ideals, which somehow contradicts our assumption, because we took B to be the biggest ideal, which was not a product of prime ideals, contradicting our assumption. Okay, great. So every ideal can be written as a product of prime ideals. Now let's just check that this representation is unique. So lastly, let's prove that the representation is unique. When I say representation, I mean the representation has a product of prime ideals. So suppose we have, say, P1, P2 to Pn being the same as Q1 up to Qm with Pi and Qi not necessarily distinct prime ideals. So I can have repetitions on each side. Then what does this mean? Then we need that Q1, this product, for example, has to be contained in P1, because P1 divides this, clearly. P1 divides this, the right-hand side, and so division turns into inclusion, so we have this, this means we have this inclusion here, which means P1 contains some of Qi, one of the ideals, some Qi. see that we saw this before. See proof of lemma. What's it? 3.3.4 to see why this is the case. So by relabeling, we can assume that Q1 is contained inside of P1. But now these are two prime ideals, and in the Dedekind domain, all prime ideals are maximal. So we can't have a containment of non-trivial prime ideals, non-trivial maximal ideals. So they must be the same. So, since all prime ideals are maximal, we must have Q1 equals to P1. So now, if you go back to our assumption, we had a product like this with P1, and now we know that P1 and Q1 are the same things. And now we want this corollary that we had before, we can cancel out the first ones and then just continue. So now, corollary? What was the number of this? 3.3.13. We can cancel out to P1, and we get you get P2 to Pn equals Q2 to Qm, and you continue like this. Let's do this again now. You're gonna get that n equals m, and after relabeling, Qi equals Pi, which completes the proof. So notice that when we first saw uniqueness factorization, we had this statement about units. We could say that the two things were the same up to a unit, but because we're in ideals, the ideals somehow absorb the units. So we don't need to worry about units in this case because we're just moving ideals. So great. In a Dedekind domain, every ideal is a product of prime ideals uniquely, so which means in a ring of integers, every ideal can be factorized uniquely into a product of prime ideals. We'll start playing around with this more next time, but I'll finish part 2 here.